NASA has discovered a planet that could potentially support life. It is bigger than Earth. Liquid water could exist on the surface.
A newly discovered celestial body has piqued the interest of astronomers. The name of this extraterrestrial entity is TOII 715b, and it boasts dimensions approximately 1.5 times the size of Earth. It is therefore called a SuperEarth. Its proximity to our solar system is remarkable. It lies just 137 light-years away from us. For comparison, most exoplanets are hundreds of light-years away, while other space phenomena, such as black holes and nebulas, normally circle thousands of light-years from our cosmic neighborhood. This naturally raises the question, what exactly is this planet we've stumbled upon? And is this incredible planet hospitable to life? What does it mean for the search beyond our solar system? An exoplanet. Exoplanets are celestial bodies orbiting stars other than our solar system and have become the fancy of scientists since the early 1990s. Such extraterrestrial worlds, which were discovered, held a raft of intriguing possibilities for future exploration. The prospect of shooting pictures of those remote planets and possibly detecting evidence of life other than on Earth has fueled an intensifying scientific interest. NASA's mission named Tess is an abbreviation for Transiting Exoplanet Survey Satellite, the main mission of which is to detect planets circling stars. This breakthrough initiative has led to recent findings that have sent astronomers into a tizzy. One of the newly discovered star systems is TOI 700, which has been found to host 4 celestial bodies, including potentially habitable Earth-sized planets. These findings have significantly advanced our understanding of the possibility of extraterrestrial life beyond our solar system. Yet, it is also important to point out that our present knowledge of the search for life beyond our cosmic domicile is severely limited. The prevalence of life in the universe remains one of its biggest mysteries, while the exact determination of those areas most likely to support life remains an unattained holy grail. Undeterred, researchers remain hopeful in their belief that the stipulations necessary for the design of a habitable planet prototype will be delineated. This is the equivalent of asking a young sketching artist to draw the perfect partner. The ideal exoplanet candidate would have to fulfill all of the following: being a terrestrial body, or in other words, much like Earth, having a thin atmosphere, having a size similar to that of Earth, harboring liquid water, being at a distance from its host star such that its biosignatures could be studied, orbiting around a star with stable energy output. Heavy elements would have to be in similar proportions to our own solar system, and enough time would have to have passed such that noticeable changes in the biosphere could take place. The first requirement for life to arise is a proper stellar companion. If a star is too massive, its evolution will take place too quickly, and there will be little time for life on its surface to get underway. On the other hand, if the star is a much less massive red dwarf, the planet must be in a very close orbit to receive enough stellar radiation. Its atmosphere would also be in danger of being stripped away by intense stellar flares. It is in the long-term possibility of habitability that this delicate balance is realized. Arguably second in importance to the first is the composition of the planet in question as a vital discriminator. It is by seeking out worlds with solid surfaces that could support human life and atmospheres thin enough to allow air-breathing organisms like ourselves that scientists find the probability of discovering an Earth-similar planet greatly increased. It means that, for size and mass, planets must be just right. There are no overly large or too small planets. The ones that are too big have many too thick atmospheres in which life as we know it would find survival very difficult. On the other hand, planets that are not big enough cannot hold an atmosphere at all. While findings show that any Earth-like size of a planet should be approximately about 2 times the diameter size of our Earth, with an addition of about 30% so far, more than 5,000 exoplanets have been discovered, but only a few of them fit the tight conditions for possibly supporting life because of their larger sizes and volatile atmospheric composition. Most of the Earth-sized exoplanets discovered so far are too hot, uncomfortably close to their stellar companions and hence beyond the definition of a habitable zone. These results highlight the challenge in the search for life beyond our cosmic backyard. Notwithstanding these challenges, scientists continue to explore distant worlds with the tempting hope of finding extraterrestrial life. It has taken them to fascinating discoveries in space and disclosed the secrets of the universe, one celestial body after another. But how do scientists determine if a planet like TOI 715b could actually support life? It all comes down to one key concept: habitable zone. The habitable zone, mostly known as the Goldilocks region, is a theoretical concept designed by scientists to come up with an estimate of the optimal distance from the star where a planet might possess the right condition for liquid water. Although not wholly accurate, the notion serves as a useful tool in astrobiology and exoplanetary research. The boundaries are decided based on the consideration of factors relating to the body's type, reflectivity, and finally, overall mass. However, one needs to realize that being in this zone alone does not guarantee the definite existence of liquid water on the surface of the planet. There has to be a proper atmosphere with certain chemical compositions for actual habitability. Over the years, these definitions have been refined to come up with a more critical definition known as the conservative habitable zone. This finer model was introduced in 2014 and sought to narrow down the best candidates for maintaining liquid water. By applying this more precise criterion, researchers will have drastically reduced false positives in their mission to identify potentially habitable worlds. It was based on the comparative amount of energy received by a planet from its parent star relative to Earth. More specifically, the rocky planets receiving between 40% and 85% of the solar radiation that Earth receives are considered to be in the CHZ, not taking into consideration their distance to the star. The method allows the scientists to focus their search effort on a planet where liquid water and with its life might, with more reliability, be found. It has to be stressed that, inasmuch as the CHZ does indeed give a very fine sneak preview for habitability, it is usually an indicator of habitability that is probabilistic rather than predictive. Other parameters that come into play and are very influential in the determination of a planet's habitability include atmospheric composition, geological activity, and the presence of organic compounds. While there are many complexities, the habitable zone is perhaps one of the most defining concepts in astrobiological scholarship, bringing together a wider range of investigations into the prospects of life out there and our place within the universe, red dwarf. This exoplanet orbits a small red dwarf star, to be precise, of the M-type main sequence star. It is a kind of celestial body, much unlike our companion Sun in size and temperature. About a quarter the size and mass of our bright yellow giant, but if placed within the habitable zone, it has a better chance for life forms that may be. Compared to our brilliant yellow dwarf, red dwarfs have long lives, providing plenty of time for simple organisms on their planet's surfaces to evolve. This particular red dwarf is older than our star companion, with an estimated age of about 6.6 billion years, while our Sun-like star is a mere 4.6 billion years old. Its low magnetic activity renders it harmless, while its siblings have been known to undergo periods of high flaring, which can actually strip other orbiting bodies of their atmospheric envelopes. While a few planets in its vicinity have tenuous atmospheres, this little red dwarf seems to have burned itself out trying to do so. The red dwarfs are the prime targets in the search for extrasolar worlds that may harbor life. Our SuperEarth orbits extremely close to its stellar companion, completing one orbit in just 19 Earth days. Because the star is small and the planet is so close to the star, transits come along quite frequently, yielding crisp views that will be easy for major new telescopes such as the James Webb Space Telescope to study for an atmosphere. The James Webb Space Telescope will introduce new phases in our understanding of those faraway planetary bodies lying beyond our solar system. Have you ever thought about being able to tell what gases make up the atmosphere of an object lying several millions of light years away? The James Webb Space Telescope is going to help us find planets that could potentially support life. It is now working on the determination of whether TOI 7115b has an atmospheric envelope. If it does, its atmosphere might be easier to spot compared to those planets that are composed of a lot of denser and drier atmospheres. That would, in turn, fuel more interest in its potential to harbor life. There is also some speculation about another planetary body in this system that could be positioned within the habitable zone. While still hypothetical, this would put the planet at approximately the size of Earth if it is confirmed to exist. It would also make it the smallest exoplanet ever discovered by this telescope in a habitable zone. This might just turn into an enormous discovery of importance, extending our knowledge of options for life in space and demonstrating an enormous variety of planetary models that support it. Oceans. One of the interesting things about TOI 715b is its peculiar characteristic. It cannot just have water on its surface, but it needs to be a fully aquatic planet. As an ocean planet, it can be a mesmerizing celestial body containing a large body of water on its whole surface, or it may have subsurface oceans. In many cases, it contains no large dry land areas since the water can envelop everything. In other cases, the whole planet can be drowned by liquids of a different nature than water, such as lava or ammonia. The main problem connected with exoplanets outside our solar system is that with the current technology, we are unable to see the surface water directly. Therefore, scientists have to use a creative method to possibly detect the presence of liquid water. They use the atmosphere to search for signs of water vapor that would hint that liquid water might lie beneath the surface. One of the concerns about these distant worlds, of course, is whether or not they might host life. Though we hope extraterrestrial life forms are not leviathans, monstrous creatures, our models do indicate that planets with oceans might be quite common in our galaxy. That is a discovery that does open very exciting possibilities. There may be many oceanic worlds out there still waiting to be found, furthering our understanding of the universe and possibly revealing new avenues for scientific exploration and research. Radius gap. That means TOI sits in what's called the small planet radius gap. If we were to line the planets up, we would realize there are those bigger and smaller than Earth. But there's a pretty notable lack of planets, just about 1.5 to twice as big as our terrestrial home. Where have these celestial bodies disappeared to? This is interesting to astronomers because it tells them how planets form and evolve with time. This is actually an important concept considering that planets do not simply not form in this size regime. They form larger and then lose mass, a bit like a balloon losing air over time. This could be a process driven by gravitational interactions between the planets and their parent stars, wherein the latter strips some of the former's mass. At the same time, it orbits around the former, as our Sun does with cometary debris. The cosmic map riddled with those mystery gaps is full of enigmas, and such planets, much like our newly discovered SuperEarth, are the potential keys to unraveling those mysteries. However, it was still not known if this is an occurrence outside our solar system, especially regarding the red dwarf star. Some scientists again hypothesized that this could be due not to the size, but to the different densities of the planets. If this is done to a newly discovered exoplanet, the research can be infinitely more exciting, as this may reveal some secrets about the nature of the other star and its companion planet. This exciting discovery opens up new directions of research that might lead to a number of path-breaking findings in the fields of astrophysics and planetary science. While trying to ascertain the nature of such mysterious gaps, researchers could get secret hints related to basic processes controlling the formation and evolution of celestial bodies within our cosmos. Tess. By contrast, Tess is an orbiting satellite launched into our celestial neighborhood by the U.S. space agency NASA almost 7 years ago. It has proved to be an astronomical success story with the discovery of thousands of exoplanets outside our solar system. While the usage of Kepler had to do more with finding larger planetary bodies, Tess was designed to focus on finding smaller Earth-like worlds, possibly orbiting nearby bright stars. Such a strategic change in focus would allow scientists to study these potentially habitable planets more effectively with future observational instruments. Thus far, Tess has turned upside down our knowledge about exoplanetary systems and potentially opened doors to very great discoveries in astrobiology and interstellar exploration. The Kepler mission, now called K2, continues searching for exoplanetary discovery by transit observation, similar to the recently launched NASA Satellite Transiting Exoplanet Survey Satellite, or TESS. Given the existence of this new spacecraft, one may ask, why does Tess exist, and what is different about it compared to its predecessor? The essential difference is more philosophical. Whereas Kepler focused on the statistical analysis and mass production of exoplanet discoveries, Tess is more selective in its strategy. Kepler sought to retrieve a large volume of data concerning thousands of exoplanets. It is also purposed to obtain a result that is needed to offer a real quantification of the frequency of Earth-like planets around stars in an observable universe. It is called Eta Earth, which gives the number of stars having surrounding Earth-sized planets. However, Kepler was never designed to investigate in great detail the detailed nature of those discovered exoplanets. Instead, it acted more like a cosmic census taker, delivering periodic tallies of the exoplanet population, in effect, getting a letter in the mail every decade. But Tess is more of a neighborhood watch kind of affair. It focuses its gaze on nearby stars and only in a relatively small range of distance, zeroing in on bright stars hosting transit exoplanets. The goal for Tess was to find planets that would be optimally studied for decades to come. This philosophical difference manifests in the different approaches taken by Kepler and Tess, whereas Kepler's focus fell upon a relatively tiny wedge of the sky. It plumbed a volume of space about 3,000 light-years deep, whereas Tess covers most of the sky but only looks at stars a few hundred light-years away. Tess's approach is to survey an area over 400 times larger than that surveyed by Kepler. For this reason, Tess is particularly good at finding exoplanets of bright nearby stars. You will hear the term bright nearby stars many times in this discussion, and for good reason. It's a phrase that makes a lot of difference when it comes to exoplanetary discovery. So, what makes Tess so exceptional at finding these distant worlds? It all comes down to its innovative approach and remarkable technology, how it works. Tess is an astrophysical wonder from NASA that is sure to revolutionize our understanding of the universe. Tess hosts 4 state-of-the-art optical instruments, each of them fitted with an astonishing 16.8 megapixel sensor. These sophisticated cameras have been designed to capture wide swaths of the sky. Each covers an area 24 degrees wide enough to capture an entire constellation within a single frame. The journey of Tess falls into 2 phases. During its first year, the satellite concentrates on the southern hemisphere of the sky, and during its second year, it shifts attention to the northern parts. The space-based observer employs a novel approach in that the sky is portioned into segments, termed observation sectors, which are observed for about 27 days before moving on to the next sector. This technique gives an unparalleled resolution in the study of hundreds of thousands of stars, allowing the detection of possible new planets. Tess uses what is called the transit method for its observation of exoplanets. The idea here is that when a planet orbits a star, it sometimes passes directly between the star and Earth. When this happens, it blocks for a moment a minute portion of the light emanating from the star, which will dim it a little. Extremely sensitive photodetectors in Tess will promptly detect such minute brightness changes, thus unmasking an exoplanet's existence. Although Tess is not selective about its planetary discoveries, the leading aim is to come up with celestial bodies of sizes starting from an Earth-like planet that falls in the habitable zone where liquid water may exist to super-Jovian gas giants that are far bigger than our Jupiter. In fact, it is designed that Tess will discover thousands of new planets, many lying in systems proximate to our solar neighborhood. Thus, the planets it finds will automatically become the best candidates for more detailed scientific research. Tess will work in coordination with another spaceship, the James Webb Space Telescope, currently one of the most technologically advanced astronomical observatories ever built. The latter facility will turn its attention to the exoplanets discovered by Tess, carrying out a detailed study of their atmospheres in search of key ingredients like water vapor or signs of life. It is a dynamic duo, Tess and Webb, working together to unlock the secrets of distant worlds. Perhaps the coolest thing about the Tess mission is the fact that its sectors overlap at the poles, creating regions of the sky that are continually observed by the mission. Those areas will prove particularly useful for James Webb's detailed study, enabling scientists to zero in on the most promising exoplanets with unprecedented accuracy. Tess is dramatically expanding the insights into the universe for humanity in ways never imagined on such an unprecedented scale. Whereas Kepler was the first pioneering mission that undertook the revelation of exoplanets' diversity, it looked at a very minute portion of the sky. Tess, on the other hand, is looking across nearly the whole sky and thus becomes the most ambitious exoplanet survey mission anybody could have ever dreamed of. The fruits of Tess's labor have already started to appear. So far, the spacecraft has found hundreds of new planets, with thousands more still to uncover. Some of those planets will have conditions similar to Earth, with the potential to harbor life. Others will challenge our previous notions of what planets are even supposed to look like, massive gas giants in scorching tight orbits around their host star, small rocky worlds nestled within multiple star systems. And with so many types of planets out there, from rocky terrains to scorching gas giants, each discovery rewrites our understanding of what a planet can be. Let's take a closer look at one such discovery that's left scientists in awe. Example of Tess's discovery. One example of Tess's discoveries was the TOI 700 system. Some of the interesting features of TOI 700 are in fact captivating. While being a small red dwarf automatically qualifies it as an M-class star, it is, by all definitions and standards, a small and moderate heavenly body. It has very minute physical dimensions of about 1/3 the size of our Sun and emits light from it exactly 1/100th the intensity. Irrespective of these rather unimportant attributes, TOI 700 can be said to be a very resilient star in view of the fact that the amounts of light and thermal energy emitted on the orbiting planets are theoretically sufficient to allow habitable environments to subsist. This has made the temperature of this mystery star a very hot topic among astronomers, where rough estimates have been made at 1300 Kelvin by some researchers. The brightness of the TOI 700 becomes particularly important in our assessment of its habitability, apart from its thermal profile. While its absolute luminosity renders it faint, proximity to the other celestial bodies in its proximity makes it only about 20% less radiant, hence increasing the potential for life-bearing planets it could host. One of the key factors in assessing whether a star can support life involves taking measurements of its rotational velocity. How fast a star rotates will give any researcher an idea of the constancy of the system and, by extension, how well the environment would be conducive to a habitable planet. TOI 700 has a pretty slow rotation period, making it a promising candidate for hosting a life-friendly atmosphere. In addition, TOI 700 has a chronological age of more than 1.5 billion years, which is more than sufficient to develop a biosphere within that slender layer between the surface and the atmosphere of the planet. If life were initiated here, strong influences on the compositional nature of the planet's atmosphere may also be affected. These various factors, therefore, make TOI 700 an ideal candidate for being able to support planets with life. Coming to the planets of this stellar marvel, it was previously estimated that TOI 700 had 3 planets when the Tess mission first discovered them, whereas now it has at least 4, out of which 2 planets show promise for life. The known exoplanetary bodies so far orbiting TOI 700 are TOI 700b, a super-Earth with a radius 1.43 times Earth's, orbiting its star in 10.3 days at 0.07 AU distance from its parent star. TOI 700c, a mini-Neptune with a radius of about 2.6 Earth's radii, completes an orbit of its star every 16.1 days at a distance of 0.10 AU. The sub-Earth-sized exoplanet TOI 700d, with a radius of 1.05 Earth radii, orbits its star in 36.2 days at a distance of 0.17 AU from the star. This world constitutes the first Earth-sized habitable zone planet found by Tess. The mini-Neptune TOI 700e, with a radius of 0.95 Earth radii, orbits its star every 16 days at a distance of 0.09 AU from the star. Most interestingly, all 4 planets orbit their star within the habitable zone, meaning all of them could support liquid water and life. All these things make scientists desperately wait for a chance to study them in detail to learn more about their composition and the possibility of life. Beyond the liquid water habitable zone, an extended or optimistic habitable zone could allow liquid water to exist, although until now never mapped, on its surface for specific conditions of the atmosphere, with small adjustments to the gaseous envelope. The TOI 700 system can be thought of as a neighborhood with 4 planets or houses in it. 2 of them, TOI 700b and c, are too close to the star to support life forms like humans or animals, so there is no worry about them causing interference with life on the other planets. The other 2 planets are positioned in a place such that they could harbor human life and quite possibly be homes to some living forms. The 2 planets could be more or less rocky, positioned further enough from the star that TOI 700's stellar activity may not annihilate them. Our current investigation of TOI 700 would suggest that it has a habitable zone extending considerably beyond the location of TOI 700d. This suggests the possibility of another rocky planet residing in the star's habitable zone, which has not yet been seen because of insufficient test data. One of the most stimulating discussions is concerning the possibility of life around M-class red dwarf stars. The general case for such stars is that their planets would be tidally locked. That is, one side continuously faces the star, while the opposite side is always in darkness. The prospects for this stellar system are huge and quite exciting. Future observations with Tess will be pointed at that part of the sky where TOI 700 and its planets are located, gathering data that could eventually reveal additional planets beyond the ones already discovered. In addition, time will be devoted to the espresso instrument on ESO's Very Large Telescope to follow the star's motion over time. These observations will most likely be useful for working out the masses of the planets circling this star, especially for the innermost ones. Other studies that might be considered in the near future regarding the ultraviolet spectrum of TOI 700 may provide useful data about the atmospheric activities and features of its orbiting planets. For instance, although the planets in our universe may be super hot, they still have a habitable atmosphere. When they have large portions of carbon dioxide in their atmosphere, then the air acts like a blanket, heating up the whole planet with strong winds. The theoretical possibility for life to thrive in such environments still exists, provided the planet has enough water reserves, though challenges to thriving life are great. The closer we push with each new development of observational capabilities and technological prowess, the closer we are to finding signs of life from beyond our terrestrial home. Meanwhile, current and future observatories, such as the Habitable Worlds Observatory and the Louvois mission, continue to play a crucial role in this quest. From its base in Chile, the Habitable Worlds Observatory plays an active role in developing our knowledge of exoplanets that could host life in our galaxy. By employing a range of active imaging and spectroscopic analysis techniques, it attempts to identify exoplanets hosting life. So far, the Habitable Worlds Observatory has detected more than 20 planets within the so-called habitable zone, the region around their host star where temperatures allow liquid water to possibly exist on the surface and, by association, life. In collaboration with the Louvois Future mission, the Habitable Worlds Observatory will attempt to complement our knowledge about life on other planets. The unmanned mission launching in the 2030s will be in search of exoplanets and studying them within the galaxy. Equipped with a series of scientific instruments, it will be able to enable Louvois to deduce elements such as water, oxygen, and carbon essential for life. Furthermore, the mission might capture images of exoplanets that could indicate whether they are even potentially capable of supporting life. Another exciting possibility for the existence of extraterrestrial life comes from the star system TOI 700. This star system has a high probability of detecting life on one of its 4 planets, since all of them lie within the habitable zone of their star. With its relatively small and cool nature, the TOI 700 is right in the middle in terms of light emitted and has a very regular, though slow, rotation rate. All these factors make TOI 700 an ideal candidate to host planets that can potentially harbor life. As we continue to study further and enhance our methods, the possibility of there being life elsewhere other than Earth becomes increasingly feasible. With this, we conclude our journey of exploration of 2I-700. We leave you with this question and ask you to spell out your theories on life beyond Earth in the comment section below. Your view matters in our continued search into the mysteries of the cosmos. Thank you for flying with us through this cosmic journey of space explorations. Please don't forget to smash that like button and hit subscribe for more fascinating scientific topics.